Hi, and welcome back to Fundamentals of Engineering with Farhad, Mechanics of Materials, Saint Venant's Principle. Jean-Claude Barre de Saint Venant, late 18th century to late 19th century, was a French mathematician and scientist who did a great job in early stress analysis and also fluid dynamics. So he has a very well-known principle in stress analysis, which is Saint Venant's principle, and it just says if we have like an axial load applied by two rigid plates to a rubber model, so the two rigid cap, it just let the stress almost evenly distributed in the rubber model. But what if we just apply the concentrated load to the rubber model without the caps? It just increases the stresses at the center line, as you can see at the top. So that's exactly what Saint Venant's principle says. It just says the stress at the location of the applied load is much higher than the corners. Mhm. And also, if you have like a stress, you want to consider a stress distribution in a plate under concentrated axial load. If you just consider a column or a beam, for example, and with the width of B, and then you want to see the effect of a stress distribution under the load. It just defines like different scenarios. The first one is when you have a distance equal to the width of the plate move downward, and then when you come a bit closer to the center line of the load and also then more closer to the load, the stress distribution varies. In the first scenario, the difference between the maximum and minimum stress distribution is almost negligible, and as you move closer to the effect of load, you can see how maximum and minimum deviate from each other. And when you are very close to the location of the load, the minimum and maximum change drastically in amount, in terms of amount. And that's the same like when you apply a force above a soil. As you move deep down to the soil, the effect of the load at the top is disappearing and diminishing. So that's the case. So in the first case, when you have the height equal to the width of the plate, sigma minimum is 0.97 and sigma maximum is 1.02. You can see how they are close to each other at the depths of B. And if you move a bit closer, like a half of B, you can see sigma minimum is 0.66 and sigma maximum is 1.38. And when you move to a quarter of widths in terms of depths of um, our case in the last scenario, sigma minimum is almost zero point 0.2 of sigma average and sigma maximum is 0.2 and half. So you can see how it changed from 0.2 to 2 and half, more than almost more than 10 times bigger the is difference between sigma max and sigma min. And definitely this line stands for sigma average in all scenarios. Max, min, max, min. So that's the Saint Venant's principle. It just says how the stress distribution varies by depths or the location of the concentrated load. And another interesting concept is stress concentration. For example, if you have like a steel plate pulling it from both sides and there is a circular hole at the center of your plate. So in that case, we we have like a stress distribution, which is, for example, if you cut it from the center line and the circular hole has a radius of r and the plate has a width or depth of d, then stress concentration, it just says in the vicinity of the circular hole, a stresses increases drastically, and as you move farther to the side from the hole, the stress is decreased drastically. That's the pattern of stress distribution which you can see. Again, this is a stress distribution near circular hole in a flat bar under axial loading. So this is again sigma max, this is sigma min, sigma max, sigma min, sigma max, and sigma average. The same pattern for the bottom part. And also when you have like a fillet plate which there is a change in radius, then if you want to see the effect of stress in the fillet plate, the same story. The stress at the vicinity of the fillet is much higher, and when you move farther from the look vicinity of the fillet, the stress decreases, and the same likewise when you again approaching from the bottom part to the fillet part, the stress increases. So again, stress distribution near fillets in a flat bar under axial loading. So again, this is sigma max at the sides, and this is sigma mean at the center, and this is sigma average. The good news is that this is an example of a circular hole, and like the results, the good news is the results are independent from the size and shape of the member, the size, and also the material used for your case, and it's only depending on the geometry parameter like the diameter of the hole to the depth of your plate. So in a circular case, so then you will read a k factor based off 2r over capital D, and then read it and move up to the graph and read the k from the vertical axis. That's the flat bars with holes. And if you have a fillet example like this one, in this case the result depends on r over small d and also capital D over small d for fillets. So this is the radius of fillet, small r, d, and capital D. So it's again, if you have like a fillet plate bar with the axial load, you will jump to the flat bars with fillet and read the ratio of r over d and then d over d. You will need to read out this ratio r over d from here and then d over d based off each of these graph. For example, stand this is for d over d, and then read the k value, and this is definitely the k value from the side. Thank you. We'll solve a numeric example in both circular hole and fillet bar in next videos. Thank you.